Our solar system is located on one of the spiral arms of the Milky Way galaxy, approximately 26,000 light-years from the galactic center. The Milky Way is a barred spiral galaxy with a diameter of about 100,000 light-years, containing between 100 billion and 400 billion stars, as well as vast amounts of gas, dust, and dark matter. The Milky Way is not an isolated entity. Along with the Andromeda Galaxy, the Triangulum Galaxy, and some 30 to 40 other galaxies, it forms the local group, which spans about 10 million light-years in diameter. The local group, in turn, belongs to the Virgo supercluster, a massive structure containing about 100 galaxy groups and clusters with a diameter of approximately 110 million light-years. On an even larger scale, these superclusters form filament-like structures surrounding vast cosmic voids, resembling an enormous cosmic web. This is the large-scale structure of the universe as we currently observe it. So, how large is the universe? The observable portion of the universe is referred to as the observable universe, with a diameter of about 93 billion light-years. This is not because the actual size of the universe is limited to this scale, but because the universe is 13.8 billion years old and light can only travel 13.8 billion light-years in that time. Due to the continuous expansion of the universe, light from objects too far away will never reach Earth, making them forever unobservable to us. As for the actual size of the universe, there is no definitive answer. In the scientific community, it could be infinite, or it might be a closed surface, like the Earth's surface, finite yet boundless. The unobservable universe refers to regions of the universe whose light cannot reach Earth, primarily because cosmic expansion exceeds the speed of light. So, how large is the true unobservable universe? The answer is that it may be at least 23 trillion light-years wide. That's a 1 followed by 12 zeros. First, let's consider the observable universe. According to modern astronomical measurements, the universe is approximately 13.8 billion years old. Due to the finite speed of light, the farthest we can see is the distance light has traveled since the Big Bang, reaching us today. This range is known as the observable universe, with a radius of about 46.5 billion light-years. In other words, looking out in all directions from Earth, the observable universe forms a vast sphere, nearly 93 billion light-years in diameter. This is the most intuitive measure of the universe's size in human understanding. However, it is crucial to note that this is only the part we can see. Why can't we observe the entire universe? The limitations stem from the speed of light and cosmic expansion. No information in the universe can travel faster than light, so regions beyond 13.8 billion light-years haven't had enough time for their light to reach us. Moreover, space itself is stretching, and distant galaxies are moving away from us at ever-increasing speeds. In fact, the expansion of the universe exceeds the speed of light beyond a certain distance. When galaxies recede faster than light, their light can never catch up to us. It's important and note that this superluminal expansion refers to the stretching of space itself. an inherent expansion of the fabric of space-time, rather than motion through space, so it does not violate the theory of relativity through cosmic microwave background, CMB radiation, and isotropic observational data. Scientists have deduced that the curvature radius of the unobservable universe is at least 250 times that of the observable universe. If the observable universe is 93 billion light-years in diameter, the lower limit for the unobservable universe's diameter is 23 trillion light-years. This 250-fold factor is merely a lower bound. If the universe is finite, it must be larger than this estimate. However, it could very well be infinite. If the true diameter of the universe is indeed 23 trillion light-years, then the volume of the observable portion accounts for less than 0.5% of the total. If the universe is truly infinite, our observable realm wouldn't even qualify as a drop in the ocean. Whether the universe is finite or infinitely expanding, it far surpasses human intuition. Our home, the Milky Way, is but one of hundreds of billions of galaxies, a mere speck of dust, and Earth is just a tiny planet, orbiting an ordinary star on the outskirts of this galaxy. If the entire universe were an ocean, the history of human civilization might not even register as a single ripple. The most daunting realization is that the answers to questions like, how large is the universe and what lies beyond it, may forever remain beyond the grasp of human civilization. Over 13.8 billion years, the universe expanded from a singularity into a vast sea of stars, evolving from elementary particles into stars, planets, and even giving rise to life and intelligence. We humans are but specks of dust in this grand cosmos, yet we possess the curiosity and courage to explore its mysteries. From the wonder of ancient stargazers to modern probes venturing beyond the solar system and telescopes capturing light from galaxies 13 billion years ago, our understanding of the universe has deepened, yet the realm of the unknown continues to expand. What is the nature of dark matter? Why is dark energy driving the accelerated expansion of the universe? Does life exist elsewhere in the cosmos? These questions await exploration by our generation and countless generations to come. When we look back from the moon 380,000 kilometers away, or gaze from the even more distant orbit of Mars, no other planet in the universe is quite like Earth. Wrapped in deep blues, gentle whites, and vibrant greens, this rocky planet is the only home known to harbor life in the entire cosmos. The surface of Earth is never still, driven by tectonic movements. It continuously undergoes dramatic transformations, seas turning into land and land into seas. The entire crust is divided into 6 major plates, floating like giant puzzles on molten magma, moving slowly at a rate of a few 2 to 20 centimeters per year, a speed comparable to the growth of our fingernails. Yet, over time, it brings about earth-shattering changes. When two plates collide, the crust is compressed and uplifted, forming towering mountain ranges. The Himalayas, for example, are the result of the Indian plate pushing northward against the Eurasian plate. When two plates pull apart, the crust fractures and sinks, creating rift valleys and oceans. The East African Rift Valley is a product of such separation, and it may eventually form a new ocean in the future. if plates slide past each other. Earthquakes are triggered. The frequent earthquakes and volcanic activity in the Pacific Ring of Fire are due to the constant interaction between the Pacific Plate and surrounding plates. Volcanic eruptions are also a powerful force in shaping Earth's surface. When magma in the mantle accumulates enough pressure, it breaks through the crust and erupts onto the surface. The lava released during eruptions cools to form volcanic rock, piling up into volcanic cones. Meanwhile, the massive amounts of gases and water vapor released provided essential materials for the formation of Earth's atmosphere and oceans. 71% of Earth's surface is covered by oceans. This water originated from early volcanic eruptions and the melting of icy comets, gathering in the low-lying areas of the crust to form vast oceans. The presence of oceans, in turn, provided an ideal breeding ground for the origin of life among the 8 planets in the solar system. Earth is neither the largest nor the closest to the Sun, yet it possesses a series of just right conditions that allow life to emerge and thrive. First, its location in the habitable zone. Earth is about 150 million kilometers from the Sun, a distance that keeps the average surface temperature neither as scorching as Mercury nor as frigid as Mars, allowing liquid water to exist stably. And liquid water is essential for life. Second, the protection of the atmosphere. Earth's atmosphere extends about 1,000 kilometers high, primarily composed of nitrogen and oxygen. It not only provides the oxygen necessary for respiration, but also blocks harmful ultraviolet radiation from the sun, while regulating surface temperature through the greenhouse effect. Greenhouse gases like carbon dioxide and methane in the atmosphere trap heat radiated from the ground, keeping the surface warm and preventing drastic temperature fluctuations. Without the greenhouse effect, Earth's average surface temperature would drop to minus 18 degrees Celsius, turning the entire planet into an icy wasteland. Then there is Earth's magnetic field acting like an invisible shield, deflecting high-energy charged particles from the solar wind, preventing our atmosphere from being stripped away. Without this magnetic field, Earth might have ended up like Mars, losing its atmosphere and becoming a barren world. Additionally, Earth's mass and gravity are also just right. Sufficient mass allows it to hold on to its atmosphere, unlike the Moon, which lacks an atmosphere due to its weak gravity. Yet the gravity is not overly strong, making it manageable for life to thrive. The convergence of these conditions has made Earth a rare oasis of life in the universe. Over 4.6 billion years, Earth has transformed from a molten fireball into the vibrant blue planet we see today. Its interior hides a fiery core. Its surface bears the marks of tectonic movements. Its atmosphere shields us from harmful external elements, and its liquid water nourishes all living beings. We humans are but fleeting guests in the long history of this planet's life. From the emergence of humanity to the present, merely a few million years have passed, a mere blink in Earth's 4.6 billion year timeline. Yet it is this planet's generosity and gifts that allow us to survive, develop, and explore today. As we reflect on Earth's past and seek to understand its structure and mysteries, we do so not only to satisfy our curiosity, but also to learn to cherish this unique blue home in the cosmos, and to treasure every patch of land, every drop of water, and every breath of air it provides. The most fascinating and awe-inspiring celestial object in the universe, the black hole, invisible and intangible. It devours all matter that approaches it. Not even light can escape its gravitational pull. From Einstein's prediction to direct observation today, it took humanity a century to barely uncover the tip of its iceberg. What exactly is a black hole? Simply put, a black hole is an object with extremely strong gravity, so powerful that even light, the fastest entity in the universe, can escape its gravitational reach. It is called a black hole because it neither reflects nor emits any light, making it impossible to observe directly. However, we can detect it indirectly by observing its effects on surrounding matter. For instance, it pulls nearby stars and gas, forming a hot accretion disk that emits intense X-rays, which serve as crucial clues for scientists in locating black holes. Black holes are not born as they typically evolve from the death of massive stars. When a star with over 25 times the mass of the Sun exhausts the hydrogen fuel in its core, nuclear fusion reactions cease without the outward pressure generated by fusion. The star's core collapses rapidly under its own gravity. This process triggers a violent supernova explosion, whose brightness can even outshine an entire galaxy. If the collapsing core is sufficiently massive, gravity becomes too strong for any force to counteract, ultimately compressing it into a black hole. Additionally, black holes are not purely consumptive. According to Hawking radiation theory, black holes slowly emit energy through quantum effects and may eventually evaporate, though this process is extremely slow. A black hole with the mass of the Sun would take far longer and the current age of the universe to vanish completely. Black holes also possess other remarkable properties. For example, they warp the space-time around them, much like a heavy stone placed on an elastic mattress causes it to sag. The immense mass of a black hole creates severe curvature in space-time. If someone could approach a black hole purely hypothetically, they would experience time slowing down. To an outside observer, a person crossing the event horizon would appear frozen in that moment forever. Black holes are the most extreme objects in the universe, challenging our understanding of physical laws, while embodying humanity's boundless curiosity about the mysteries of the cosmos. From the predictions of Einstein's general relativity to the release of the first black hole image in 2019, our understanding of black holes continues to advance. Yet they still guard countless unsolved enigmas. Humans possess an innate desire to explore the universe, but our physical bodies cannot traverse the vast sea of stars directly. This is where a group of special envoys embark on missions on our behalf. They are satellite probes from low Earth orbit to the edge of the solar system, from lunar exploration to asteroid visits. These unmanned devices have carried human curiosity through the cosmos for decades. The exploration map of satellite probes spans the solar system with different detection targets requiring tailored exploration approaches. For instance, to explore the Moon, a probe must overcome Earth's gravity, precisely enter lunar orbit, and some must even achieve a soft landing. Mars exploration poses even greater challenges. At its farthest, Mars is over 400 million kilometers from Earth, requiring probes that travel for over half a year to reach it. While also surviving the Mars-7 minutes of terror, the critical descent from atmospheric entry to landing, where a series of maneuvers including deceleration, parachute deployment, and hovering must be executed within just 7 minutes, with almost zero margin for error. When exploring gas giants like Jupiter and Saturn, probes must endure extreme radiation levels. Satellite probes are unmanned spacecraft equipped with scientific instruments, primarily categorized into two types: orbiters and landers. Rovers. Orbiting probes act as reconnaissance aircraft in space, entering the orbit of target celestial bodies for long-term orbital observation. Equipped with cameras, spectrometers, and other instruments, they capture surface images, analyze atmospheric composition, and measure magnetic field data, continuously transmitting scientific data back from Martian orbit. Landers and rovers, meanwhile, serve as landing forces, touching down directly on celestial surfaces and even moving across them to explore. Examples include lunar rovers and Mars rovers like Curiosity and Perseverance, which can collect rock samples on site, probe surface environments, and provide us with the most direct information about these celestial bodies. Beyond these, there are also flyby probes and impactors. Each type of probe has distinct responsibilities, working together to accomplish exploration missions. Though these probes may appear compact, they carry profound missions, mapping topographic features of celestial bodies, analyzing atmospheric and soil composition, searching for signs of water and life, studying magnetic and gravitational fields, and even returning samples to Earth. Each task helps expand our understanding of the universe. To fulfill these missions, probes must be equipped with several core technologies. First is the power system, mostly reliant on solar panels for electricity, while probes venturing far from the sun use nuclear batteries. Next is navigation and attitude control technology, enabling precise positioning in the vastness of space and adjustment of flight orientation. Then there is the communication system, capable of transmitting data from billions of kilometers away, with even faint signals captured by ground stations. Finally, the scientific payload, an array of precision instruments serving as the eyes and ears of the probe, responsible for collecting and analyzing data. Our solar system, like a bustling family of planets, revolves around the sun at its center, with 8 planets, moons, asteroids, and other celestial bodies orbiting it in orderly motion. First to appear are the 4 rocky planets of the inner solar system. They are solid planets composed of rock and metal, closest to the sun and nearest to Earth. The first is Mercury, the smallest planet in the solar system, only slightly larger than the Moon. It is the closest to the Sun and experiences the most extreme temperature variations in the solar system. What makes it even more remarkable is that a day on Mercury equals 59 Earth days, while a year lasts only 88 days. In other words, on Mercury, a single day lasts 2 years. Next is Venus, known as Earth's sister planet, It is similar in diameter and mass to Earth, but its environment could not be more different. Venus is enveloped in a thick carbon dioxide atmosphere with an extremely severe greenhouse effect, making it even hotter than Mercury, the hottest planet in the solar system. Even more intriguingly, Venus is the only planet in the solar system that rotates in reverse, spinning from east to west. If you were to observe the sun from Venus, it would rise in the west and set in the east. The third is our Earth, the only planet in the solar system known to nurture life. It is protected by a thick atmosphere and a magnetic field that deflects solar winds. These just right conditions have made Earth a life oasis in the cosmos. Earth also has a natural satellite, the Moon, which stabilizes Earth's axial tilt, drives the tides, and serves as Earth's most vital companion. The fourth is Mars, the familiar red planet. Its surface is covered with iron oxide, giving it a reddish appearance. Mars has about half the diameter of Earth, a thin atmosphere composed mainly of carbon dioxide. It boasts the solar system's tallest mountain, Olympus Mons, and the largest canyon, Vales Marineis. Moreover, traces of dried riverbeds on its surface hint at the possible presence of liquid water in ancient times. Beyond Mars and the asteroid belt lies the outer solar system, the domain of the four gas giants. They lack solid surfaces, are composed mainly of hydrogen and helium, and far surpass the inner planets in both volume and mass. The first is Jupiter, the largest planet in the solar system. Jupiter is a gas giant with no solid ground, only thick layers of gas, and a core likely made of rock and ice. Its most famous feature is the Great Red Spot. Additionally, Jupiter has 79 known moons, among which Ganymede is the largest moon in the solar system. Even larger than Mercury, the second is Saturn. Renowned for its stunning rings, Saturn's rings are composed of countless ice chunks, rock fragments, and dust. Yet they are incredibly thin, measuring only tens of meters in thickness. Saturn has the lowest density in the solar system, lower than that of water. If there were an ocean large enough, Saturn could float on it. Its mass is 95 times that of Earth, and it has 80 known moons. Among them, Titan is the only moon with a thick atmosphere and features liquid methane lakes on its surface, making it a candidate for potentially hosting life. The third is Uranus, notable for rotating on its back. Its rotational axis is tilted at an extreme 98 degrees, as if it were rolling sideways through the solar system. Uranus's atmosphere is mainly composed of hydrogen, helium, and methane. Methane absorbs red light from sunlight, giving Uranus its unique blue-green appearance. The fourth is Neptune, the farthest planet from the Sun and the coldest in the solar system. Neptune's atmosphere also contains methane, imparting a deep blue color. Its storms are far more intense than Jupiter's, making it the planet with the fastest winds in the solar system. Neptune's mass is 17 times that of Earth, and it has 14 known moons. Among them, Triton is the only large moon in the solar system with a retrograde orbit, likely a captured object from the Kuiper belt. Finally, let's talk about Earth's natural satellite, the Moon. The Moon is Earth's only natural satellite, and the fifth largest moon in the solar system. Its rotation period matches its orbital period, so we only ever see one side of the moon. The lunar surface is covered with craters, vestiges of asteroid impacts from the early solar system. The moon's gravity causes Earth's tides and stabilizes Earth's axial tilt, providing essential conditions for the emergence and evolution of life on Earth. From scorching Mercury to frigid Neptune, from massive Jupiter to diminutive Pluto dwarf planet. Every planet in the solar system is unique, holding clues to the evolution of the cosmos. Some are fiery, some icy, some solid, some gaseous. Together they form the solar system we call home. Humanity's exploration of these planets never ceases, from probes flying by Jupiter to rovers landing on Mars. We are gradually unveiling their mysteries. These planets are not just celestial bodies in the universe, but also beacons guiding human exploration of the cosmos, inspiring us to journey ever onward. In humanity's journey to explore the universe, there exists a group of brave pioneers. They leave the embrace of Earth, venture into the vast sea of stars, measuring space with their footsteps, witnessing the grandeur of the cosmos with their own eyes. They are astronauts, a special profession known as spacewalkers. Becoming an astronaut is akin to being one in a million, requiring passage through three major challenges: physiological, psychological, and skill-based. First is the physiological challenge. An astronaut's body must be top-tier. Vision must meet standards. No chronic diseases are allowed. Cardiopulmonary function and cardiovascular systems must far exceed the norm. And even dental health is strictly examined, because in the weightlessness of space, a minor toothache could lead to major problems. Even stricter are the special physiological tests, enduring centrifuge training at 8 times the force of gravity, simulating the hypergravity environment during rocket launch, adapting to hypoxia in low-pressure oxygen chambers, preparing for potential cabin leaks, and undergoing vestibular function tests to avoid severe space motion sickness in orbit. Additionally, there are strict limits on height and weight, generally requiring a height between 160 to 185 centimeters, with proportional weight to fit both spacesuits and the confined spaces of the space station. The psychological challenge is equally crucial. Astronauts must work for months in closed, isolated space environments, requiring immense stress resistance, emotional stability, and teamwork skills. Psychological testing employs various simulated scenarios to assess emergency response, decision-making, and communication abilities. Only those who remain calm in extreme conditions can pass the evaluation. Finally, the skill challenge. Astronauts must possess solid scientific knowledge in fields like astronomy, physics, and engineering, along with mastery of spacesuit operation, spacecraft piloting, and emergency rescue skills. They must even learn multiple languages to collaborate with international counterparts. Every space mission undertaken by astronauts carries humanity's dream of exploring the universe. The scientific experiments they conduct in space help us study life phenomena and materials science and microgravity, providing invaluable data for medical and aerospace advancements. Their observations and explorations of space deepen our understanding of cosmic mysteries laying the foundation for future interstellar travel and Mars colonization. From Yuri Gagarin becoming the first human in space in 1961 to Neil Armstrong stepping onto the moon in 1969 to today's multinational astronauts living aboard the International Space Station, astronauts have used courage and wisdom to gradually turn humanity's space dreams into reality. They are not merely participants in space exploration, they are symbols of the human spirit, embodying curiosity about the unknown, fearlessness in the face of challenges, and persistence in pursuing dreams. In the future, as space technology advances, more astronauts will journey into space, visiting Mars, asteroids, and even more distant cosmic realms. Their stories remind us with dreams, courage, and perseverance, humanity can continually push boundaries and stride into the vastness of the universe.